The Unix and Linux operating systems utilize the setuid and setgid access rights flags to allow users to execute programs with the permissions of the owner or group of the executable file. These flags also enable users to modify behaviors in directories. Often employed to grant temporary elevated privileges for specific tasks, setuid and setgid permissions are essential for operations requiring different access levels than those assigned to the user by default. For instance, tasks like altering system files or databases to change login credentials necessitate these flags to execute successfully. Sometimes the need for elevated privileges might not be immediately apparent, such as in the case of the ping command, which relies on these permissions to send and receive control packets on a network interface. In file modes, the setuid and setgid bits are commonly denoted by the values 4 and 2, respectively, in the high-order octal digit of the file mode. This configuration, for example, would appear as 67111, indicating that both the setuid and setgid bits are set, 4 plus 2 equals 6, with read/write/execute permissions for the owner, 7, and execute permissions for the group, ast1, and others, 1. While some systems use a symbolic representation like U equals RWX, Go equals X, UG plus S for these bits, Chmod typically lacks a recursive mode tailored for directories. As a result, altering permissions in an entire directory tree often entails manual intervention, such as using the find command in conjunction with chmod. The system typically prevents the invoking user from changing the new process in any way to prevent potential security exploits, such as using trace, LD library path, or sending signals, although signals from the terminal are an exception. Misusing the setuid attribute can indeed introduce security vulnerabilities if assigned to poorly designed executable programs. Some operating systems opt to disregard the setuid attribute when applied to executable shell scripts due to security concerns. The presence of setuid executables is why non-root users on Unix are unable to access the CRUT system call, illustrating the security implications. When the setgid permission is set on a directory, any files and subdirectories created within inherit its group ownership instead of the primary group of the process creating the file. This inheritance applies only to new files and subdirectories created after setting the permission. Existing files and directories are not impacted, including those moved into the directory afterward. This approach allows for collaborative file handling within a user group without explicitly adjusting permissions, under the condition that existing file permissions remain unchanged. The setuid permission on directories is largely disregarded in Unix and Linux systems, with FreeBSD being an exception, where it can mimic setgid behavior, ensuring all new files and subdirectories in a directory are owned by the directory's owner. However, this functionality is typically not necessary on BSD-derived systems, as directories are treated as if their setgid bit is always enabled by default, maintaining consistent ownership of new files with the containing directory. This behavior aligns with the principle stated in Open2 that new files inherit the group of the directory containing them. The setuid feature, while beneficial in specific scenarios, can pose security risks if misused, leading to possible exploitation of elevated privileges. For security reasons, the system typically restricts the invoking user from modifying the new process through methods like ptrace, LD library path adjustments, or signaling, although terminal signals remain permissible. Consequently, the utilization of setuid executables impacts the availability of certain functionalities, such as the CRUT system call for non-root users in Unix environments. Conversely, implementing the setgid permission on a directory results in files and subdirectories created within inheriting its group ownership, deviating from the primary group of the creating process. This inheritance policy exclusively applies during the creation phase, affecting future files and directories. Existing files and directories present at the time of setgid bit assignment, or those moved into the directory afterward, remain unaffected. This functionality facilitates collaborative file work within a user group without explicitly defining permissions, adhering to the security expectation that existing file permissions should not alter implicitly. Notably, the setuid permission set on directories does not impact most Unix and Linux systems. However, FreeBSD can be customized to interpret setuid akin to setgid, enforcing ownership of files and subdirectories within a directory to belong to the directory owner, a rudimentary form of inheritance. This interpretation is usually unnecessary in BSD-derived systems, as directories are inherently treated as if their setgid bit is consistently enabled, regardless of the bit's actual status. This behavior aligns with the principle stated in Open2, where newly created files inherit the group of the containing directory. The octal and alphabetic permissions of files or directories can be viewed using the command line tool stat. For an executable file owned by root with swid permission, like /usr/bin/pest, when executed, it runs as root, allowing modifications to files restricted to normal users. In contrast, SGID permissions ensure that directories inherit the group ownership of the parent directory, such as when Torvalds creates a directory, electronic, under a parent directory, music, owned by root and group engineers. The group ownership is automatically set to engineers due to SGID. Without SGID, the primary group of Torvalds, would have been assigned ownership. Moreover, the sticky bit, illustrated by directory video games owned by Torvalds and group engineers, prevents users like Wozniak from deleting files they don't own within a directory with group permissions, deterring unauthorized deletion. This is exemplified by Wozniak being unable to delete Tekken under video games. In another scenario, when Torvalds creates a file or directory, thoughts, with sticky bit and SGID set, Wozniak cannot delete, rename, or move thoughts. However, being part of the group allows Wozniak to edit the file. Combining sticky bit and SGID can enforce restrictions even further, possibly with a read-only UMask or an append-only attribute. These mechanisms ensure security and controlled access within a Linux system.